In this video, I will show you how you can use the new formulas we have to prove that two random variables are not independent. Well, let me recall from the point that what are two independent random variables? X and Y are independent if you remember for any a value, x value a, and for any b value for y, the probability of intersection of the event is equal to probability of product y equals to b, and this should be true for all a value of x and b value of y. And we did some examples in the unit 1 of 3.4 and showed that, well, basically what you need to do is that you have to do a table for probability of x being equals to ai's on the first row and probability of y being equal to bj's for all these things, and then you need to do probability of x equal to ai, y intersect with y equal to bj. Well, and then you form this table. Basically, this is not just one. There is a number of things here, number of things there, and then you form this table. And we saw that x and y are independent if the table is actually times table, meaning that every point here in the middle is product of these two. We're basically checking that thing boils down to showing that. But well, in those examples, we saw that this takes a lot of time. Here now we want to use the fact we just learned to do a little bit quicker, maybe in some cases. What is that fact? The fact says, sorry, let me just put a box here. Fact says that if x and y are independent, then you can conclude this thing: e of xy is equal to ex ey. And also for all a and b's, for all constants, v of ax plus by is equal to a squared v of x plus b squared v of y. Yes, so these are two very good implications of independent random variables. Now, let's say I have two random variables x and y. So let's start with this point. Two random variables are given, and we know that for two given random variables x and y, we somehow know, we either know the numbers or we are given the fact that e of x y is not equal to ex ey. If someone gives us a pair of random variables x and y such that, and we know that exy is not equal to ex equal to ey, what could go wrong? Well, the only thing could go wrong is that the assumption of this statement is not satisfied. In other words, from this, we can right away conclude that x and y are not independent. Right away, we can conclude that. This is the new approach. Sometimes computing all those values in that table, in this table up there, is not easy. It just takes more time. But somehow, if we can find these kind of information and compare these ones and see that they are not equal, we have a statement saying that, well, this x and y are not definitely independent. So let me just write the new approach. What do we do? Someone gives us two random variables, x and y, and then what we do, we go check if exy is not equal to ex ey, then we can conclude that x and y are not independent. And similarly, if a v of a x plus by is not equal to a squared vx and b squared by, for some constant a and b, then right away we can conclude that x and y are not independent. So this is the approach we will take in some of the problems. In the problems that computing these parts are possible and we can do and check that these are not equal. Just before I leave, I just want to remark that it is very important to understand that if exy is equal to ex times ey, you cannot conclude. This is not a good action to do. That if this equality is true, you cannot say that x and y are not or are independent. In other words, the test we are independent. This cannot be used. What this fact can be used for is to show that these are not independent. Check the equality is not true, then you can conclude that these are not independent. And if this happens, then you can say that, well, these are not independent. The other way around is not true. If this equality holds, you cannot say x and y are independent. So this is something that we will do in some examples in this unit, and you will see that sometimes it's a very good, strong um, a tool to check that two random variables are not independent.